Hello, my name is Kerem Arıkan, and today I'm going to be presenting secure caches for compartmentalized software. This paper is a collaborative effort between authors from Binghamton University and UC Riverside. First, let's give a brief background on our motivation. In a typical software development scenario, a primary developer might hire a third party to speed up the development process. They collaborate on a monolithic application, where all code shares the same memory and privileges. This model assumes ambient authority. Any code can access any resource. That's a problem, because malicious or buggy third-party code can freely access sensitive information and potentially leak it. To address this, researchers have proposed compartmentalized software, where code is split into isolated compartments with limited privileges. Each can access only specific memory regions called domains. In this example, domains 0 and 2 are private to the main and third-party authors, while domain 1 is shared. In such an environment, secret data can be protected by revoking access to private domain 0 for the third-party compartment. In this paper, we exclusively consider compartmentalized architectures where domains have page-level granularity, where every page belongs to a single domain. Such systems often require hardware changes. The memory management unit, for example, or the MMU, is provisioned with a permission table that retains which compartments have which access rights to which domains. Page-level granularity of these systems also requires the TLB to extend its entries with domain metadata of that page. When a memory access is performed, the address translation returns the translated page's domain information. This domain information is then subjected to a sanity check where the domain metadata is compared against the permission table to see if the currently running compartment has access to that domain. However, a major issue lies in the hardware. CPU caches don't enforce domain boundaries as the memory does, opening door to side channel attacks. For example, compartment 0 might access secret dependent data X. Compartment 1 then can access data Y that collides with X in the cache space and use timing to infer the secret's value. Indeed, cache side channel attacks in multi-component software environments have been demonstrated in prior literature. We present 4 examples here. First, compartmentalization architectures like Intel SGX have been shown to be prone to L1 cache side channel vulnerabilities when the attacker and the victim enclaves are located in hyperthreads of the same core. Second, different website clients can be executed within the same browser engine process. An attacker client can use this multi-component environment to probe the cache occupancy fingerprint of the victim client. Third, graphics libraries have been shown to leak secrets through separate function calls between an attacker and a victim within the same process. And fourth, an untrusted OS kernel can leak secrets through caches using powerful capabilities like single stepping within the same process. Cache partitioning is a principled and deterministic method for blocking side channels. Each mutually untrusted code portion is isolated in the cache space. This way, an attacker's partition cannot collide with the victim's partition. But there has been no effort to implement side channel partitioning in compartmentalization systems. To adapt partitioning to compartmentalized software, we introduced secure caches for compartments, or SCC for short, a cache isolation mechanism that partitions the cache into domain-isolated regions. We tackle this design from 3 different angles. First, we introduced the notion of domain-oriented partitioning, a novel cache isolation method. Common partitioning mechanisms partition the cache into code-oriented regions. However, intense data sharing between compartments creates significant implementation and coherence issues when the setup is employed. Let's investigate the following example to understand this problem better. In this setup, the cache is split into code-oriented regions, meaning that compartments 0 and 1 are each provisioned with a single partition while domains remain in the memory. Here, compartment 0 performs a write to the shared cache line in its partition. This modifies the state of the data, which is shown as shared star. Later, compartment 1 performs a read to the same shared cache line. However, since the read access results in a miss, the cache should retrieve the shared line from the memory or lower level structure. This means that compartment 1 has just read a out-of-date version of the shared line. Such read after write interactions, thus, between compartments result in aliasing, coherence, and implementation issues like this. In response to this problem, we present domain-oriented partitioning, where cache partitions are based on domains instead of compartments. In this figure, private data X and Y cannot collide in the cache space. Since domain 1 here is shared among these compartments through intentional permission delegation, shared data is not subject to side channel protection. Now let's follow the prior example in a domain-oriented setting. Again, compartment 1 performs the same write to the shared line. This time, the write is performed inside the shared line's corresponding domain partition, which is domain 1 in this case. Compartment 1 now performs a read, which retrieves the correct modified version of the shared line, since domain-oriented partitioning prevents data sharing-related aliasing. Thus, preventing duplicate instances provides a simpler partitioning implementation and a more elegant way of maintaining cache coherence while establishing side channel protection. Second, since untrusted compartments may run sequentially on the same core, SCC must isolate private caches like L1. But adding domain-oriented remapping logic here can increase the L1 access latency. This is a major challenge, since higher-level caches incur higher performance degradation to the system when additional remapping logic is implemented. Here, we show how an unoptimized cache partitioning approach would cause additional overhead. In the meantime, we also show how SCC implements its remapping logic. SCC utilizes two hardware resources to establish partitioning, the TLB and a domain remapping table, or DRT for short. We assume that the baseline compartmentalization architecture already includes domain metadata of each memory page in its entries, as we previously discussed. Modern caches adopt virtually tagged physically indexed caches, which normally allow the TLB and the cache to be simultaneously accessed. Unfortunately, in this unoptimized scenario, TLB has to be accessed before the cache for SCC to retrieve the remapping information of the domain. Then, we access DRT to retrieve the remapping metadata of that domain. Then we perform a set access, and the access is finalized by the tag matching process. Notice how the unoptimized access takes 4 cycles instead of 2 cycles of a baseline cache. To mitigate this overhead, we make a key observation. Compartments tend to access the same domains for extended periods. The graph here demonstrates the percentage of consecutive cache accesses of the same domain. On average, consecutive domain accesses account for more than 98% of total accesses. We call this phenomenon domain access locality. To exploit domain access locality, we can essentially store the most recently accessed DRT entry to speed up the cache accesses. Now let's look at an optimized cache access in the light of this new information. Here we introduce a new structure called Active Domain Register, or ADR for short. ADR stores the DRT entry of the most recently accessed domain, domain 0 in this case. This allows SCC to access the cache and the TLB simultaneously. If ADR predicts the domain correctly, the cache can then perform tag matching as usual. In summary, if not optimized, SCC incurs 2 additional cycles to the cache access. With ADR, we achieve the same baseline cache access latency in case of a hit. In case of a miss, however, SCC incurs the same latency as an unoptimized cache. As a third angle to SCC, we introduce mechanisms to stop library-based side channel attacks that bypass simple domain isolation. Here, we show how library-based side channel attacks are possible even with SCC. First, the victim calls an insecure function in shared library. This in turn fetches the function's instructions into the library's domain partition in the cache. Later, the attacker calls the same function with a set of arguments to infer which secret values were used to call the vulnerable function prior to the attacker. Since both the attacker and the victim use the same cache space to call the library function, side channels are still present even with SCC. This shows that such attacks are still possible even under partitioning. In response, we introduce horizontal partitions that preserve a per-caller library state for each domain's partition, for a single domain's partition. This prevents cache collision between different callers of the same function. So let's examine the same attack scenario we presented, now with horizontal partitions. Now, the victim performs its call, which loads the library instructions into its own partition. When the attacker attempts the same inference technique, it cannot collide with the victim's instruction residue. This disallows the attacker from measuring the cache timing. Thus, maintaining different cache states for each function caller effectively mitigates library-based sidechannel attacks. So far, we only discussed SCC's intra-process security guarantees. So let's also briefly discuss how SCC extends to multi-process environments and how it establishes security in said environments. Here, we see a 2-core CPU. Each of these cores run compartmentalized processes. When it comes to shared last-level caches, SCC makes a distinction between domain-oriented partitions and process-level partitions, or PLPs. SCC allocates nested partitions where domain partitions reside inside more conventional PLPs. The last-level cache retains a single process remapping table, or PRT, that contains the remapping information of PLPs for each core. This way, SCC eliminates both intra-process and inter-process sidechannel vulnerabilities. We now turn our attention to the methodology and the evaluation. We implement SCC in a cycle-accurate Gen 5 simulator. To generate compartments, we used the SOAP compartmentalization tool on MeBench and Spec 17 benchmarks. To generate domains, we performed a permission table generation run, which is followed by experiment runs used to obtain the actual performance numbers. To compare against SCC, we evaluated cache flushes on compartment switches. That is, when the program crosses a compartment boundary, the entire cache hierarchy is flushed in interest of security. This is shown as FOSC in this graph. Furthermore, we also implement a flush version where only L1 cache is flushed on compartment switches, while SCC is implemented on other levels. This is shown as FL1 OSC. On average, these two flushing configurations incur 60% and 32% performance degradation, respectively. Compared against SCC's average 7% performance loss, flushing the caches yields a significant performance degradation. This is due to the benchmarks with the highest compartment switch frequency exhibiting performance numbers below 30% off the baseline, even close to 0% in some cases even. This shows that cache flushing is an infeasible method for compartmentalization. We also compare different partitioning layout configurations, which are proportional and static. In the proportional configuration, domain partition sizes are proportional to the number of pages allocated for that particular domain. In the static configuration, a pre-selected number of uniformly sized partitions are pre-allocated proactively. Here, SCC outperforms both of these allocation techniques, which incur more than 25% performance loss, while SCC incurs only 7% again. Finally, we use the McPath tool to estimate hardware and power overhead. We demonstrate that SCC adds only 0.63% hardware area overhead, as well as a modest number of additional power consumption. In summary, while compartmentalized software contains intra-process attack exposure, shared hardware caches can still leak sensitive data. To fix this, we need cache designs tailored to compartmentalization. With SCC, we take the first step in this direction. We implement domain-oriented partitioning, introduce latency-aware L1 caches, mitigate library-based sidechannel attacks, and we also implement SCC in Gen 5 simulator and evaluate it on McPath, which yields 7% performance loss on average across our benchmarks and 0.63% hardware area overhead. The paper also provides a formal security analysis and further implementation details. With this, I conclude my talk, and thank you for listening to me.